Okay, let's take a look at doubling time. And so we can use the exponential growth equation to derive what the doubling time of the population is, given this equation, which is time for doubling equals the natural log of 2 divided by r. So if we know r, we can figure out the doubling time of the population. And that's done by using this equation and solving for t. So if we, t over here, this t. So if we have n equals 0, or n at 0, or population time at 0, and we just call this 2 n0, because this is double this number, we can divide out n0, and we'll have 2 on this side. Take the natural log of both sides, so we get ln2 over here equals r times t. Divide out r, and we're left with the natural log of 2 divided by r equals t, in this case time for doubling. So that's a useful tool if we want to figure out how long is it going to take for this population to double, assuming this intrinsic growth rate, this r value. And this is that populations increase by multiplication, not by addition. So even if the growth rate seems small, the population can grow rapidly. What that means is that if you start off with a population of 10 one year, and you have a growth rate of 10%, next year you'll have 11, and then next year 12.1, and next year on and so forth, where that percent is going on the current population, not your original population. So if you have a population of 10 and a growth rate of 10%, it's not adding 1 every single year, it's adding 10% of your current population. 10% is still a relatively large growth number, but we'll look at a couple examples of a few percent. 1 or 2% makes a big difference over long periods, decades. And so for human population, we can calculate the intrinsic growth rate r based on the observed growth rate of 1.1%. Meaning if we just have 2 points of data, last year's population and this year's population, and that population went up by 1.1%, we can calculate the intrinsic growth rate and then use that for the exponential growth function. You can see section 11.1 in the book, which is a calculation of this for another example. But effectively, r equals the natural log of nt plus 1. So if we're using this year and next year's analogy, or maybe we'll use this year and last year because we're using prior data. So this would be this year's population, and this is last year's population. So in this case, that's our nt in a time, and time plus 1 would be this year, divided by time, in this case a year, that we can calculate r. So we're starting with an initial population nt of 7.7 billion, and we know nt plus 1, so if this is last year and this is this year, nt this year, nt plus 1, is 7.78 billion, based on this 1.1% population growth, and their time interval was 1 year. So we just take the space in there. See, it always wants a big R. I don't want a big R. We take the natural log of 7.78 divided by 7.7. Take that whole unit divided by 1, which winds up with an R of 0.0109. So we can plug that into our exponential growth function, where n1 equals 7.7 times e to the 0.0198, or 7.8 billion. Now, of course, this is just 1 year, so we could do it by hand, but if we want to know what population is going to look like in 10 years, then we'd add a times. We'll do a shift here. Oops, that wasn't shift. Oh, shift I first. There we go. That didn't work either. Shift I. Control I. There it is. Okay. All that work just to get a italicized t times t. Then we could now use the same equation and use t as 10 and then build out what that population is going to look like over a long period of time. So that's where this becomes super useful. Okay, well, let's look at a couple kind of ideas for, in this case, lambda. The 25 deer were introduced on St. Paul Island. This is off the coast of Alaska. I actually have a friend that lives out there and works with the community out there. And they have a lot of reindeer. It's a small island. I've always wanted to go out there, but it's a pretty small island. And this initial introduction of 199 reindeer, I'm sorry, 199, 25 reindeer in 1911 has now resulted after 27 years, so that would have been 1938, the population had increased to 2,048 individuals, and now there's still a whole bunch out there. So that's a population growth rate, a lambda of 1.18, which doesn't sound like a lot, but after 27 years, they went from 25 to over 2,000, so that's a huge amount. Much higher growth rates have been observed in many species. The western kangaroos can have a massive growth rate, a lambda of 1.9. Let me just make sure. Let me check something here real quick. Yeah. Finite rate of increase through the geometric growth rate. Okay. A geometric growth rate of 1.9. Field voles, 24. Rice weevils, 10 to the 17. This is an yearly, so it's huge. Some bacteria double every 30 minutes. What was the stat in the book? It was like after some period of time, they would use up every atom in the world. But there's a reason that we're not all just overrun by E. coli bacteria. Now, there's limitations to population growth. And the two main factors we talk about that change or limit population growth and sizes through time are density-independent factors. Their effects are independent of the number of individuals on that population. And then density-dependent factors. Their effects are dependent on the number of individuals in that population. So here's two examples. I kind of want to do, this doesn't really have the words up there, which is kind of annoying. Let me see. Just make it a little clearer here. Okay. So the solid, these points are generally the populations which bounce around, our population growth rate. And so this can be thought of as like the average population growth rate. As population increases, growth rates don't change. So they could still be growing at 10% a year, independent of how many there are. Where density dependence growth rate, lambda, goes down as the population increases. And so at low populations, you could have a lambda of 1.1, or sorry, let's go higher than that, 1.5, and then eventually you're coming down to maybe a lambda of less than 1. You could even have population shrinkage depending on what's driving your density dependence. Where density independence, you could have a few organisms and they're all still growing at 10% a year. You can have lots of organisms and they're still growing at 10% a year, or a lambda of 1.1. Density-independent factors include weather conditions such as temperature, precipitation, catastrophes, floods, hurricanes, and climate change. Meaning, it doesn't matter how many mice are on a barrier island. When the hurricane comes, some of you are going to die. Doesn't matter if you were a sparse population or a dense population, the likelihood of you dying has nothing to do with that. It just has to do with the fact that a hurricane hit your little island. And so here's an example of this insect that the population size fluctuates with temperature and rainfall. External impacts, density independent factors can have major impacts on populations from size, from year to year, from size to size. Now you could argue at certain levels there's density dependence, which we'll get toward, but you can think of heavy rainfall years have a lot of plant growth. Things that eat those plants are going to increase, and that increase isn't related to the fact that there was few of them last year. It has to do with that there was a abundant food source this year, so they're able to exploit that. Here's that example here. The observed and predicted number based on the weather. That really populations are tracking weather, not tracking density of other members of their population. Gradual climate change can impact populations, increasing mortality rates in western coniferous forests over several decades. Is related to temperature increase, less snowpack, etc. So it's not that there are too many trees on the hill and they're shading each other out. It's that there's not enough water, or it's not getting cold enough to kill parasites, things like that. That are happening independent of the number that are out there. So here's an example of tree mortality rates happening in areas, in coastal areas, more so than interior areas. Mortality rate of trees per year along the year, independent of what the population is. So not related to them being overpopulated and that's increasing mortality. It's that overall the climate's not good enough to support any of them. So whether there were a few trees on a hill or the hill was densely packed, they're all still experiencing the same level of mortality due to an external driver due to climate change. And in Africa, this is an example of growth rates have dropped below a lambda of 1 due to illegal poaching. And here they're using poaching as an example that's independent of density, which can be true, meaning that it doesn't matter if there's a big herd or a little herd, you're still going to get poached. And in fact, what actually frequently happens is as populations decline, the black market value for those individuals actually goes up. But nonetheless, that's an external factor that's driven by really an external market demanding that ivory rather than some level of their population. It's not that there are so many of them that they're competing for food or resources, that they're being indiscriminately taken due to for the ivory trade. So here's a lambda of 1, and recently they've fallen below that lambda of 1. So that's cause for issue. So again, when the lambda drops below 1, geometric growth rate, finite growth rate, lambda, geometric growth rate, finite growth rate, all the same thing. When that falls below 1, that population is now declining. Population level times less than 1 times 0.9 equals less than it was last year. Density dependent factors, the amount of resources and this is like you can almost make an argument that everything has some level of density dependence on it. We're looking for like more obvious density dependent factors, i.e. the amount of food or habitat relates to some measure of survivorship, birth, death, dispersal, etc. That changes with density. That as density increases, birth rates often decrease, death rates increase, and dispersal, immigration increases, which all tend to decrease population size. So here you have to have some there's a finite amount of resources. And as the populations increased, they began to exploit that finite level of resources, leaving fewer resources to go around, leading to competition, leading to fighting, death, starvation, weak young, fewer young, abandoning young, all of these things that are decreasing the population growth rate. Now you can have the same finite resources and much fewer, a much smaller population, and now that population per capita has more resources, so they're going to grow faster, they're going to be bigger, they're going to not starve as much, they're going to have more young, they're going to be fatter young, they're going to be better cared for. All of that's going to increase the population growth rate until we start to limit out on the number of resources we have, and that's going to decrease the population growth rate. Population regulation is density-dependent factors that cause the population to increase when density is low and decrease when density is high. Density-independent factors can have large effects on population size, but don't regulate population size. Only density-dependent factors can regulate population size. So density independence is not a measure of population regulation, meaning when populations are low, density independent factors aren't helping that population grow faster. And when populations are high, density independence isn't helping reduce the growth rate of those populations. Back to the mouse on like a barrier island example. If there was a lot of mice on that barrier island and a hurricane hit, yeah, lots of them are going to die compared to if there were few mice on that island and a hurricane hit, fewer of them are going to die just because there's fewer of them there. But that's not regulating the growth rate of those individuals. It's an external factor that's independent of how that would regulate the population over long periods of time. So in songbirds, the number of eggs laid per female and number of young that survive decreased with density. If we overplant soybeans at various densities, at the highest densities, many of the seedlings died, and the density of eggs of the flower beetle, as density of the flower beetle increased, death rates also increased, and that was done in like a beaker experiment. So just examples of how when there's lots of them, there's competition or not enough resources to go around, and that ultimately relates to a reduction in population. Here are those examples here. So here's this is I like this study actually. This is the number of breeding females and the independent young per female. So they're tracking a population through time, or rather through density, and they've got the years numbered here. So here with few breeding females, 10 to 20, even some of them kind of up to 30, each female would have 4 independent young. As the population increased to 60 to 70 breeding females, they're only having 1, maybe 1.5 on average young. So they've decreased their growth rate, where prior at low densities, 1 female would have 4 young. At high densities, 1 female is having 1 young or 1.5 young. And they were able to manipulate this environment by adding food to a certain part of the population, and that population, when presented with more food, had more babies, indicating that food is limiting, and that's the limiting. That becomes limiting when the population gets high. There's only so much food to go around. Each individual in that population is getting less food. We can circumvent that by adding more food, and then those individuals are no longer resource limited, and they can now support more young. This is the soybeans showing kind of a leveling off here. This is the density of surviving plants. If there's a 1-to-1 survival line, we'd expect every plant you plant to survive, which is true at low densities, and then as density gets higher, it starts to level out that a certain plot of land can only support a certain density of plants. And so if you put more than that in there, then all the extras wind up dying. So egg density per tube, mortality rate. So if you put a few eggs in a tube with some flour, the beetles are happy. If you put lots of eggs in the beaker with some flour, most of them die. When birth, death, and dispersal rates show strong density dependence, population growth rates may decline as densities increase. If densities become high enough to cause the finite growth rate, or lambda, or the geometric growth rate, high enough to cause it to become 1, or the intrinsic growth rate to become 0, the population starts growing. If they decrease further, the population declines. I think like the next graph is better than that. Okay. So here's population growth rate, lambda. 1 is stable, right? And finite growth rate, geometric growth rate, doesn't really matter. 1 is not growing. 2 is basically doubling every year. This is the density of plants, low, medium, high. And at lower densities, plants have a higher population growth rate. At higher densities, plants have a lower population growth rate. This is Daphnia. They're kind of something called water fleas, I think. But they're pretty cool. Oh, it's a different P.W. Frank. Okay. Yeah, he wasn't doing 1915. Interesting. Okay, so here's the density. 0 is maintaining population. Negative, this is R here, intrinsic growth rate. Negatives are declining populations. 0 is maintaining, and then greater than 0 is increasing population. Here's a log scale. So the density of Daphnia at low numbers, 1 to 4, you have a high growth rate. It tends to cross the threshold from growth to stability to negative population growth at around, this is showing 24 is below that. So when you've got more than 24 Daphnia per cubic centimeter per milliliter, which is a lot, growth rate goes down, meaning death exceeds birth. So this population will decline, and ideally eventually it'll move over here and start to grow again. And if it grows too much, then the population will start to decline, move back here, start to grow again. So you can imagine kind of a cycle there. Ideally, we want stability. And stability is thought of as the carrying capacity. So we can look at a logistic growth model. So instead of the exponential geometric growth model, we can look at a logistic growth model. And this incorporates carrying capacity, which is the maximum population size that can be supported indefinitely by the environment. So this is based on availability of habitat or food or other resources. There's a carrying capacity for that environment. And as the population reaches that carrying capacity, the growth rate's going to slow down. So the population nears it, but ideally doesn't exceed it. And so at carrying capacity, the population growth rate would be 0. In theory, at carrying capacity, the population growth rate would be 0, and the population would just maintain on a perfect plane in perpetuity. As we learned about in the prior chapter, there's a bunch of annoying things about environment and variability that kind of prevents that. I might break here. Trying to see how much more I've got to get through. Where are we? Logistic growth. Yeah, I'm going to break here, and I'll restart. I'll probably have to say that again. I'll restart with the logistic growth. And then we'll take that probably through to the end here. But there's another big chunk here. All right, we'll come back for chapter 11C.